kind of triangulate between the schedules of the people who are joining us on the webinar, and then everyone here who tends to run 10 minutes behind the hour. We're going to split the difference and go ahead and get started at 2:05. So I hope that's okay, and we may have a few people coming in, but
sure.
Somebody just point them at the chairs, and I think we'll be okay. Don't point them at the ginger ale. That's mine. I want to welcome you all to the second NSSC webinar of the semester. Cameron Geddes is a scientist at Lawrence Berkeley National Lab in the Bella Center, and he's using lasers to make high-intensity, quasi-monoenergetic gamma ray sources, which is pretty cool. So I'll let him tell you about that.
Great. All right, thank you. Like some of you here, I was a graduate student in the Cal Department of Physics, and I didn't stray far. I just went up the hill, and I've been working on developing a technology for very compact high-energy particle accelerators for the last 15 years. And for the last few years, we've been looking, as Bethany said, into how we can apply that to make more precise gamma ray sources than are currently available. So that's what I'll talk about today. And the talk will be in a couple of different parts. I'll start with a sort of qualitative motivation for why you might care about a photon source in general and why you'd want it to be monoenergetic. And then I'll actually present the results of two different projects that we have going. For the last 2 years, we've had a study. I'm a plasma physicist, so this study has not been my work primarily. It's been the work of people who work in photon beam applications to look at what such a source could do and what parameters it would need to have in order to deliver benefits for nonproliferation applications. And if you're in those kinds of applications, I certainly invite your input and look forward to talking to you about that. And then the second part is more my bread and butter, which is how would you use a compact particle accelerator to make a better photon source? And that starts out with a compact way of accelerating particles to high energies. And the experiment that we have underway to combine that, you don't just need a particle accelerator, you need a way of producing photons. And we do that by scattering a second laser pulse from the relativistic electron beam that we've created. And you need ways of tailoring that electron beam that I'll talk about after you accelerate it, of focusing it, and then of guiding the laser so that you can effectively interact this scattering laser with the electron beam. And then finally, you need to get rid of the electrons that you've created so that you don't accompany your beautiful monoenergetic photon source with a giant bremsstrahlung source that will contaminate everything. So that's what I'll go through today. So in general, the reason you want a photon source is that passive methods are great. You'll use them wherever you can because they are the easiest to apply. They raise no concerns about radiation or anything like that. But many targets that we care about for nonproliferation, such as, for example, a truck, are thick enough that it can be difficult or impossible to detect or characterize nuclear materials by passive methods alone. And so if you have a chunk of material in a truck like this, particularly U-235 has low energy passive emissions. And so it could be easy to shield it from passive detection in something of that size. And so what's done is to use active methods, photon sources. And I apologize, the contrast on these slides is going to be poor, so I'll try to talk through the diagrams a little more than I otherwise would. What this shows is a bremsstrahlung-based photon source being used. The photon source sits here, shines photons through the truck, and then there's a detector array on the other side. And there are, of course, many other applications that are of interest, things like fuel safeguards, where you'd like to know what's in a fuel assembly, accident scenarios, where in something like Fukushima, there may be material melted together that you'd like to analyze the interior of. Treaty verification, where someone presents you with something that they assert is a weapon, and then presents you with something that they assert are the pieces of that weapon disassembled. Have they been honest? Can you verify that and understand what's happened? And then, well, what I'll focus on today is really non-proliferation related applications. Photon sources, really just X-ray machines, get used all across industry and medicine. So you've all had a medical X-ray, and we do the same thing for things like turbine blades to find cracks or understand how material processes have gone on. And the kinds of advantages that I'll talk about pertain to those types of applications as well. So at the highest level, what we're talking about is that we have some nuclear material inside a black box, again, in principle, large enough that the shielding would be sufficient to hide it from passive methods. And we shine in photons, and we could detect fission signatures, so-called photofission or photon-induced fission. We could look in transmission at radiography to look at the areal density of the object. And we could look at nuclear resonance fluorescence, either in transmission or the same way here in scattering. And that's in general the most specific signature. And the way that that's done now is with these so-called bremsstrahlung photon sources, where we use a radio frequency accelerator to accelerate an electron beam, slam it into a high Z target, something like tungsten or copper. And in that high Z target, the electrons collide with nuclei and emit gamma rays. And some of the collisions are very close to the nucleus, so they produce a very high energy photon. That produces this tail of the distribution out here that extends up to the electron beam energy. But most of the electrons make much more gradual collisions, and so the bulk of the emission is at lower energy. So this is sort of a characteristic of a bremsstrahlung source. So the asset of this kind of source is there's a very modest accelerator requirement. If you want a few MeV photons, which is appropriate to doing radiography or photofission or nuclear resonance fluorescence, photons in the 1 to 10 MeV range, then you need a 1 to 10 MeV electron accelerator, and that's something that's about this big. It's an industrial commodity. You can buy it. It's relatively inexpensive, and it's relatively easy to procure. But the penalty, of course, is that broad energy spread. And the continuous spectrum means that most of the photons aren't useful. If, for example, you wanted to look at excitation of fission, that centers at about 15 MeV for uranium and for plutonium. But if that's 15 MeV, then most of your photons are useless. So that contributes unwanted dose, and it can contribute noise that contaminates your material, and it can limit your ability to discriminate between different materials because your signature isn't very, very specific. In addition, these kinds of sources emit their photons both into a broad angular distribution and from a relatively large millimeter scale, not 10 centimeter scale, but millimeter scale emission spot. And that limits the ability to mitigate scattering contributions. If you have a thick target like a truck, photons will scatter through it, and that can really affect contrast. So how could you address that? First, you could control energy. So first, you could think about radiography. So radiography is nothing more than measuring attenuation through an object. And the colored curves here represent the attenuation cross-sections of different materials, from uranium to lead to iron to carbon. And they all have a sort of a knee here around 2 or 3 MeV, where they're all pretty similar, and then they spread out at higher energies. And so a bremsstrahlung source typically provides most of its photons in this range where the attenuation cross-section is very high, and therefore they don't do much good. So you're really sensing with these photons out in the tail of the distribution, and even those photons are spread across a wide range of energy. So if instead you could target your energies and select maybe an energy that's close to this minimum point, and an energy where all of the materials, various cross-sections spread out, you could much more finely discriminate between materials, and you could do it using fewer photons, that is less dose. And dose is a main constraint in a lot of these types of applications. For example, if you're looking at cargo scanning, you have to keep the dose to the target low enough that you wouldn't harm a stowaway, for example. And there are other similar requirements in other applications. If you're in a treaty context, you're not going to be allowed to contaminate the room or to endanger personnel who are nearby. Similarly, for photofission, these curves illustrate the giant dipole resonance that for various elements of various isotopes, plutonium and uranium, and they all peak around 15 MeV. And again, with a bremsstrahlung source, you're generally sort of using the tail of this distribution, and so most of the photons are useless. Whereas with a monoenergetic source, you could in principle put all the photons on resonance and be much more effective. Lastly, nuclear resonance fluorescence, which I don't show a picture of here, is a very highly specific signature. There are lines that are specific not only to element but to isotope, but they're very narrow in energy width. And so having a narrow energy width and a adjustable energy source is a high priority. But you wouldn't just care about the energy and energy spread. So this says you want a monoenergetic source and one that you could change the energy of. But the angular spread turns out in many cases to be even more important. So this is a simulation showing what happens when I put an initially very narrow. It would be a single pixel on this screen, a photon beam going through on this axis through a piece of steel. And the piece of steel is sitting here indicated by the black bars, and it's 20 centimeter thick. And you can see that the beam very rapidly blows up, essentially. It scatters very heavily in the target. And the result is that your contrast gets really degraded if you have a beam. This is a single line. You could imagine if I put multiple lines corresponding to a source that has a broad angular spread, all of those convolve, and that degrades your resolution. Whereas if you have a narrow angle source, like this red line here, if you go far enough away, you end up getting good contrast because the scattered photons scatter into wide angles. Right at the output here, they're almost buried in the scattered photons. But as you go further and further away, the unscattered photons don't diverge, while the scattered ones do diverge. So there's almost as strong of an incentive to have narrow angular spread as there is narrow energy spread in many cases. So that's sort of the basic motivation for what we do. So let me pause there. This is sort of the first little segment of the talk, and ask if anybody has questions or things to discuss. All right, very good. We'll go on. So the next thing that I want to present is the results of that application survey that I talked about. And as I mentioned, while some of this is done by those of us who are photon source developers, most of it's done by applications and signature people. And at Berkeley, that's been led by Bernhard Ludwig, also with a lot of involvement from Brian Queter and John Valentine. And the other names on this list are essentially the photon source developers for the project that I'll talk about next. And at Livermore, the work was led by Marianne Descal. She led the radiography portions and the cargo screening portions. Glenn Warren at Pacific Northwest led the treaty verification portions. Matt Kinlaw at Idaho National Laboratory led the applications for looking for concealed material, something like a parked vehicle that you suspect might have material in it. And Cameron Miller, who's a CBT student at University of Michigan, along with Bernhard, led the portions on nuclear fuel safeguards that I'll talk about. So the project started by going out to people in the laboratory and then in the agency user community and asking, well, what problems do you have that aren't solved by current methods where you could use a new capability? And it's a pretty long list that got identified, but the top four are the ones that I just discussed. That is screening and interdiction, where you have a cargo container or something similar that you're pulling through a port. Detection of hidden nuclear material in something like a parked vehicle or another similar scenario. Treaty and dismantlement verification of nuclear warheads, that's typically with a treaty partner. And safeguards. And there were a lot of applications in safeguards actually, but the one that came to the top of the list was once nuclear fuel is used, it has to be stored somehow. And one of the ways that that's done, in particular in countries that don't have or that haven't yet stored their fuel in permanent repositories, is so-called dry storage casks, where a number of fuel assemblies are put into a cask. And one of the concerns is these are generally above ground, and while security on them is very good, if you lose continuity of knowledge on one of those casks, you want to be able to verify what's inside it. And that's difficult to do because they're very large and very thick. And there are a variety of other applications that came up that I won't talk about in detail, things like emergency response and nuclear data and other applications in safeguards. So let me start with cargo. So the idea here, again, is that you have a truck that you're pulling through, and you want to know what's inside it. And you start, in that kind of case, with radiography. And the key challenges, as we've talked about a little bit already, are dose, both to the target and to potential stowaways, and also scattered dose out to the environment. For example, port personnel, how big of an exclusion zone do you have to have around this thing to guarantee that nobody walks in and gets dosed? Contrast, impacted by the scattering issues that we talked about. And Z discrimination, that is the ability to discriminate, is this aluminum, steel, lead, uranium? And that goes to the kinds of ability to select energy to discriminate different elements on that attenuation curve that I showed you. So, for example, if you want to pull a truck through, the demands are pretty tight on throughput because DNDO and the Customs and Border Patrol agencies that would actually be implementing this thing can't afford to impede commerce. And so the requirement would be that you'd want to pull a truck through at almost a meter per second while getting a 1 centimeter resolution image of it. And if you think about what that would require, you can do one of two things. What's done currently with bremsstrahlung sources is that they make a broad divergence beam that sort of covers the truck in the vertical direction, and then they pull the truck through in the horizontal direction. But that has the scattering problems that we talked about when the target is thick. And so what we looked at here was contrasting that approach with scanning of a narrow divergence beam across the target. And that's the kind of beam that I'll show you the source we're developing would produce in the future. But that would require, if you wanted a 1 centimeter beam to raster across, it would have to have low divergence, milliradian divergence, and it would have to have a very high pulse rate in order to accommodate both vertical scanning and the pull through at 80 centimeter per second. And you'd have to have a lot of photons to get through 20 to 40 centimeters of steel. But the benefit is you'd address those scattering issues, and additionally, you could adapt dose to attenuation. That is, if there's a thick thing in here, and all the rest of this is thin, which of course you can't see, but you can put few photons here because there isn't need to penetrate through very many photons. And then when you get to a thick object, you can deliver more photons to further mitigate the dose. So the simulations that Marianne did used standard objects that have been developed by DNDO for evaluation of radiography. These are the so-called CARS objects that were developed for tests of advanced bremsstrahlung system. And this shows you an example, as a first example, neglecting scattering. So this is just a more quantitative illustration of that utility of having multiple energies to look at the contrast between different materials. So this is one of the most challenging examples. Object 4 is a uranium sphere inside a lead cube. Uranium and lead are very hard to discriminate. Inside a Lexan cube, and the Lexan cube provides a large attenuating and scattering body around. So these lineouts show you the results for a bremsstrahlung system in blue. You can see that there's almost no contrast. And for various pairs of monoenergetic source energies in red, green, and black. And you can see that for the red beam, which is a 9 MeV and a 3 MeV MPS, so using those two energies, 9 MeV and 3 MeV in monoenergetic beams, you can pull out some contrast even for this very challenging case. And for less challenging cases, this is yellow cake in concrete, which is a much greater contrast. Of course, the bremsstrahlung system there then does get some contrast, but the contrast with the monoenergetic source is much greater. So then what about when you include scattering? So then it turns out that to control scattering, it's the beam divergence, not its energy spread, that's actually the important parameter. And the reason turns out to be all of those low energy photons that the bremsstrahlung source produced, they're harmful because they impart dose. But when you go through a thick steel or lead or uranium object, all of those get absorbed. And so they're not actually contributing that much to the signal or harming the signal that much. On the other hand, as we looked at in that simulation of scattering, if you have a very narrow divergence beam, you can control scattering. That is, you can exclude the scattered photons from your measurement. Whereas if you have a broad divergence beam, you can't. And so these are results quantifying that. So with a narrow divergence beam, you can see the contrast is very high for either a monoenergetic source or a bremsstrahlung beam. It's about 0.9 in both cases. And you do get a little bit of advantage from a monoenergetic source, but it's not really compelling. In contrast, if you go to a fan beam or even worse, a broad divergence cone beam, and here by broad divergence, we only mean 1.5 degrees. So it's not really very broad. But your contrast drops extremely rapidly. And this is actually not a hugely challenging target. It's only 20 centimeter of steel. If you think about a cargo system, it's much more typical to have this cargo container not empty with a dense thing in the middle of it, but filled with stuff. So what happens if you fill it with stuff at about the density of a typical cargo container? Then even this fan beam drops down to a contrast of about 0.3. So that's really the reason why there's a high priority on developing a source that has narrow angular spread. And you might say, well, if I've got a broad angular spread source, I can just put a collimator on it. And you're right. And it's very well known that that's what you do with the bremsstrahlung source if you want to take a very high quality imaging. The folks out at Livermore do this. The penalty is if you have a broad angular spread source and you collimate it down to a narrow angle, you've thrown away almost all of the photons. And so the penalty is that the rate goes way down. So what we'd really like is a source that delivers a lot of photons into a narrow angle to start with, because that source will then enable us to sort of have our cake and eat it too. That is high quality and high rate at the same time. So once you've done radiography, if you're able to improve radiography, you could improve the precision with which you identify regions that are high in atomic number. But radiography will never tell you whether something is yellow cake or it's highly enriched uranium. For that, you need something else. And that would be either photofission or nuclear resonance fluorescence. You need something that's sensitive to the element or the isotope actually being fissile. So photofission is the easier of those two to excite. And the reason is that that giant dipole resonance of photofission is very broad. It extends from 6 MeV all the way up to around 20 or above. And it centers at around 15. So you don't have much trouble targeting it. That is, your source doesn't have to have a very narrow energy spread. And the dose per fission can be much, much lower. It can be from a factor of 10 lower to, in cases of cargo where you're really restricted in the energies that you're allowed to use, can be as much as a factor of 50 lower. And if you wanted to detect, for example, a common target that's used by DNDO is a 2-kilogram piece of uranium that's shielded. If you had a photon source of a few 10 to the 11 photons per second, you could do that in seconds. And so it could be almost part of your regular sort of run-of-commerce scan. If you wanted to really do isotope identification, then nuclear resonance fluorescence is the most powerful technique. And I'll talk about this technique more when we get to detection, and this technique more when we get to tree verification. But because the widths of the lines of nuclear resonance fluorescence are very narrow, whereas this would tolerate a tens of % spread photon source, this really needs something at the percent level or below. So that pushes the source technology a lot harder, as we'll see when we come to that portion of the talk. If you had such a source that could get you to % level energy spread or less, then again, you could detect kilogram level quantities, but you would still take longer to do nuclear resonance fluorescence than this. It would probably be minutes to do nuclear resonance fluorescence. The payoff of this is that this can identify very specifically 235, 238, exactly what isotope it is, and in principle, it can even tell you enrichment. So we did 4 applications. I've focused quite a bit on cargo screening. I'm going to skim over a couple of other applications quickly and then come back to a last one. So if you had a scenario in which you didn't have the ability to do radiography, that might be something like a parked vehicle. And that's of interest for things like if you're responding to an emergency, you have something that you don't know what's inside. There you can't use radiography, but you can use photofission. And the results are similar to what I just talked about. So here you're suspecting that there's some problem with a vehicle and you want to know, is there actually, for example, a device inside it? And so now you scan your beam across and you look for photofission signals in each location. And the indication is that if you had a monoenergetic source, again, you're able to deliver more photons on resonance, more effectively probe the signature. And for source yields in the range of 10 to the 11 or 10 to the 12 photons per second, you would be able to penetrate a variety of types of shielding up to about 30 centimeter of thickness. And you can vary the shielding because in this scenario, really what you want to know is, I've got a box. Can I tell you that there isn't anything inside it, right? So you have to essentially do a calculation that tells you that no matter what the shielding is, if I know it's only so thick, I could tell you if there was something inside it. And so for that purpose, we evaluated a whole variety of shielding possibilities. And for example, stainless steel is very hard on photons. Lead is very hard on photons. Borated poly is very hard on neutrons, attenuates them very strongly. And so, for example, this lead and borated poly sandwich or layered construct is one of the most challenging shieldings to penetrate. It's the reason we selected it. So briefly on treaty verification, then the interest here again is that you're given components that someone tells you are a warhead, and then you're given components that they tell you are a dismantled warhead. You want to verify whether that's the case. And really here, because you need to verify that something is either highly enriched uranium or weapons-grade plutonium, nuclear resonance fluorescence is really the appropriate technique, because you want to specifically guard against substitution, for example, with a less enriched target. You could make that mistake with something like photofission. So here you have your sample, and you want to be able to probe whether, for example, a warhead would be an assembly of some weapons material with some explosives. You want to be able to probe both of those. And so these are examples of looking at doing that for relevant thicknesses, a few millimeters of material up to tens of millimeters of material. And with a monoenergetic source, again, you would be able to do that in minutes, which is compatible with the kinds of objectives for this kind of application. So this application, it turns out, doesn't actually require much in the way of photon source flux. You don't need a lot of photons on target because you're limited. You stimulate a process here and you have to detect the photons, in this case with a high purity germanium detector. So you can't afford to put too many photons on the detector or you will get pileup. And this, unlike the cargo's case, we assume that it's not a semi you're being presented with, it's something that's of a relevant size for a weapon. So you don't have to deal with as much shielding. And the result is that you don't have a high demand on flux, but you do have a high demand on the source energy spread. It has to be very narrow. Another thing that people are interested in is the ability to make very precise measurements. So in cargo radiography, we're not really interested if there's something that's a micron wide. Right? We're looking for bulk samples of material, things that are of the order of a centimeter. And for that, the kinds of photon spot sizes that a bremsstrahlung source produces are completely appropriate. But for other applications, if you were, for example, looking at weapons in the stockpile and you wanted to know their precise condition, you would care about resolution. And the same could apply in a treaty context. So then it's interesting to ask, could you improve the resolution? And the primary driver for radiography resolution, as probably everyone knows, essentially you're doing point projection imaging. You have a source, you have an object, and you have a detector. So the smaller your source is, the finer the resolution of the resulting radiograph. And so these simulations assess that, and in fact, the candidate source that I'll show you produces all its photons from a spot that's less than a micron in dimension. And these simulations do nothing more than verify what your intuition would tell you, which is that changing the source from which the photons come from a millimeter in diameter down to a micron in diameter correspondingly changes the radiography resolution and allows you to access micron level features. And the thing about these simulations that's a little bit less obvious than that is that they included effects of scattering and other effects that are important for targets like this, and you can still preserve that effect. So lastly, safeguards. If you have a dry storage cask, this is an illustration of one. It's a steel canister with a concrete encapsulation, and inside it, there are bunches of fuel assemblies. And so the question is, if you were to lose continuity of knowledge, you don't know anymore what's inside that cask, can you find out with a photon source? And so we did two different types of scans, and again, this was Cameron and Bernhard and their work. The thing that you would like to do, the easiest thing to do, would be to shine the photon beam along the axis of the cask. Because now if someone removes an assembly, you'll have a clear line of sight down the cask and the attenuation will change by orders of magnitude. And that's what this shows here. Through the pin, you see almost nothing. If there's no assembly, you see a big signal. And if you're going through the gap between pins or through the guide, you get a moderate signal. And so in this case, by scanning across the top of the cask here, with a very narrow divergent source again, your source has to produce a beam whose diameter is comparable to the size of a pin, so a few centimeters, to be sensitive to this effect. But you could sense the absence of a single pin. Of course, the problem is that many casks are stored in the way that they're pictured. They're stored vertically. And so then it's going to be all but impossible to scan this way. So you have to get your detector under and your source over the cask. And so you could ask your storage facility to rotate the cask for you. They're not going to want to do that. So the question is, could you do something by looking across the cask? So in this case, you're no longer looking along a pin. And so really what you're doing is you're taking an integral across many assemblies. And so this is an example of one of Cameron's simulations doing that. This is a cask that has 68 assemblies in it. And the yellow outlined ones were removed one by one. And then in each configuration, that is with all the assemblies present, with this one absent, then with that one absent, and so on, a photon beam was scanned across the cask. And the results, essentially, this is photon beam intensity transmitted through the cast as a function of angle. So you go from here up to here. And so the black is with all of them present, and then the various colors are removing individual assemblies. And so you can see that it's not at the same location, of course. If you remove this one, you get a spike in transmission here. If you remove this one, you get a spike in transmission there. And so that's what these are, right? So this is top right missing, and sure enough, there it is, right? So you get a spike in transmission at that location. And you could sense that. And the reason for this bar here is that that's about the sensitivity threshold, accounting for the background the fuel induces in the detector. That's the background that you would be sensitive to with a reasonable photon source. So that's a brief summary of the sort of simulations that we've done to look at what would you require from a photon source to be able to address these types of applications. So for radiography, the answer is you need selectable energy to be able to scan across those attenuation curves for different elements. You don't need very narrow energy spread because all of those cross sections, they vary gradually with energy. So you need to be able to select, for example, 4 and 9 MeV, but you don't care if it's a very narrow band. And that could get you lower dose and higher contrast, as well as higher yield for photofission. If you're able to push the energy spread down to about 2% or below, you could enable nuclear resonance fluorescence to do things like treaty verification or for cargo screening, that's sort of secondary screening. And it's worth noting that nuclear resonance fluorescence continues to get better as you drive the energy spread down. If you could drive it down below 0.1%, you'd enable doing material assay and enrichment type information. And if you had a narrow divergence pencil beam, that is a narrow diameter beam going through the target, you'd be able to reject scattering to increase contrast, and you'd be able to do these kinds of transmission measurements on massive objects like casks. And it would also allow you, as you scan through a target, to put dose just where the object is thick and to reduce dose elsewhere. And most of these applications fall in sort of a common range of photon fluxes in the sort of 10 to the 9 to 10 to the 12 photons per second range, repetition rates in the kilohertz range. And a little bit of that is sort of input, right? I mean, people at one point promised that with an accelerator, you could, from an aircraft, fly over a village and say if there's nuclear material there. And if you look at what the dose required to do that is, you would end up melting holes in buildings before you told whether there was nuclear material there. So applications like that got excluded based on initial considerations. And so I'm not showing those to you here. And the other input here is that there are several photon source technologies under development. I'll show you one in a moment. But they sort of fall in this range as well. So both because you don't want to melt holes in things, and at a lower level than that, you don't want to dose people with lethal amounts of radiation, this is an appropriate range. It also matches to some of the sources that are quasi-realistic, at least. So that's the conclusion of talking about how you might use this kind of source. So things that people have questions about at this point? Yeah, please.
I'm wondering, what's your biggest challenge to actually achieve such a source that you're looking for?
That's exactly what I'm going to talk about next. So essentially, the issue is the electron beam accelerator and then the disposal of that electron beam. So the key issue is that with a bremsstrahlung source, you generate photons up to the energy of your electron beam. So to make a monoenergetic beam, you have to do something qualitatively different. And the choice that we made was so-called Thomson scattering. That is, you have an electron beam, you counterpropagate a laser, some of the laser photons scatter off of the electron beam and are upshifted to high energy. So the advantage of that is that your scattered photon energy is determined by the input electron beam energy and the input laser photon energy. It's just a relativistic scattering. And the penalty of it is that the photon energy scattered is much less than the electron beam energy, at least in the regimes that are of interest here. So you need a much higher energy electron accelerator. And then once you've created those high energy electrons, you have to find a way to deal with them. I should say there are other technologies under development, the primary one of which is a so-called nuclear reaction source, where, for example, you bombard a solid target with a ion beam and induce nuclear reactions. And that creates specific lines that correspond to that particular nuclear reaction. The differences between the sources are a Thomson source is arbitrarily tunable in energy and produces narrow divergence beams. The nuclear reaction source is governed by its reaction and is isotropic. Those are the reasons why we picked the source we picked to address these needs. But if you were to do nuclear reaction source, then your challenges are different. Then your primary challenge is really a very high current ion accelerator to generate the ions to impact that target. And then secondarily, because the emission is isotropic, but you typically want a directed beam, then you need a very good collimation system in order to throw away essentially almost all of the force. Make sense?
Yeah.
Good. Other questions? Yeah, please.
As you're focusing at the higher energies, and you need a more powerful power source
Right.
than you have now, how are you keeping the machine like active, especially for like the more scale down?
Right. So that's actually what I'm going to get to in 2 slides. So if I can postpone that question for just a moment. Are there any questions on the applications part? Because otherwise I'm going to get to your question on the next slide. Let's talk about sources. All right. So what our group centers on is exactly the question you just asked. So how do you generate a quasi-monoenergetic compact photon source? Well, it's by addressing that acceleration issue. And the large team at the top of this is primarily people who do accelerator physics. The people down here are detector physicists, and in particular, Yigang Zheng is a Cal student in Kai Vetter's group. So we're developing the photon source, and we have collaborators at Livermore and at Idaho working with us. So now we're on to this part, which is how do we make a more powerful accelerator? Actually, it's not technically a more powerful accelerator, but a higher energy particle accelerator in a small space. To make the electrons of an energy that you would need to do that relativistic scattering process, to intersect a laser beam with the electron beam, and then what do you do with those high energy electrons once you've used them to make photons? So this is a little bit more detailed illustration of that Thomson or Compton scattering process. And the principle, again, is that you just need a relativistic electron accelerator, make an electron beam, and scatter a laser from it. So this process is really the dominant way that people produce monoenergetic photons at high energies. It's implemented in a variety of large facilities around the world. It supplies all those properties that we talked about. You control the energy and energy spread of your outgoing photons with the properties of your electron beam. And that means that you also have tunable energy by adjusting the energy of this beam. You adjust that relativistic upshift of the laser frequency in an arbitrary way to allow you to get the energies that you want for any of those signatures. And it turns out that as you do this scattering process, the relativistic scattering process not only upshifts the energy of the photons, but it narrows their emission angle. So whereas a dipole would radiate somewhat symmetrically, the relativistic upshift causes the emission to be very forward peaked within millirad divergence angles. And by adjusting, of course, the strength of this laser, you can adjust things like the per shot flux, and by adjusting the polarization of the laser, you can control the polarization of the photons. So this is a well understood technology. Some of you has anybody here ever used or been to Higgs at Duke? Yeah, no? Yeah, okay, cool. So yeah, so Higgs is a facility that implements exactly this process. And the issue, as you pointed out, for nonproliferation applications is that Higgs is a large building. The FEL and accelerator is about 50 meters in length. And the reason for that is the distance it takes to bring electrons up to high energy. So that's really the key challenge, is can we make an electron accelerator not at the few MeV range, as you would need for a bremsstrahlung beam, but at the half GeV, so almost 50 times higher in energy in a comparably sized space. And when we do that, we don't just need gross energy, because the scattering process is governed by almost every property of the electron beam imaginable. So this is typically what the spectrum of a Thomson source looks like, and it has both an energy and an angle dependence. And so you get this kind of bow. You get maximum photon energy on axis, and that photon energy is essentially 4 times the gamma factor of the electron, so it's about half of its energy in MeV. So 4 gamma E squared times your laser frequency. That's the energy on axis. So to get few MeV photons, you need half GeV class electrons. But then what governs the spread here is a large array of factors. Of course, different electron energies will scatter at different frequencies because they'll upshift by different amounts. But also, if you have electrons going different directions, that is a little bit of divergence on your electron beam. This bow shape of the photon emission spectrum means that if one electron is going this way and emits its maximum frequency on axis, another one's going this way and emits its maximum frequency off here, that induces an energy spread as well. So you have to very precisely control your scattering, your electron beam, and also your laser parameters can also impact scattering. And when you do that, you come up with some sort of guidelines for what kind of electron accelerator you need. For radiography and photofission, 10% energy spread, electron energy spreads at the few percent and divergences at the milliradian level are appropriate. So that'll get you photofission and radiography. If you want to do nuclear resonance fluorescence, you have to go down significantly to the percent level and 0.1 milliradian electron beam divergence. And as you do that, you have to not only worry about, well, I not only need narrow energy spread photons, I need a lot of photons. And that's complicated by the fact that the scattering cross-section for this process to occur, for the laser photon to scatter off the electron, is very low. And so typically what that means is that you need a long laser pulse. That is, you need a lot of photons to interact with your electron beam. But as those of you who have had an E&M course know, if I want to keep a laser beam focused over a long distance, what that means is that its spot size has to be big. If I focus a laser to a small spot size, it will diverge again rapidly. And so that tends to waste energy, because if I need a lot of oscillations to get effective scattering, then I need a large spot size, and most of those photons aren't useful. Most of them are outside the envelope of the electron beam. And that results in, typically, the number of photons that you get, it's not linearly proportional to the laser energy you put in, it's only proportional to the square root. And so that means it's very hard to get large numbers of photons out of this process. For example, it could require 40 joules of laser energy just to get one scattering event per electron. So that's sort of the compromise that we're stuck in and that we have to try to address. And that's sort of the core of what we're trying to do in this project. So we have a few major issues that we have to address. We need a high energy accelerator at half GeV scale, conventionally a big facility. We need some way of getting around that issue of low scattering cross-section and making a large number of photons out of our electrons. And then we need to address the fact that the shielding requirement increases both with the energy of the accelerator, and if we don't do a good job of scattering, that is, if we're inefficient at scattering, that requires more electrons, and in turn that requires even more shielding. And so that's really, in past projects, what we've tried to do is to demonstrate individual techniques to address each of these big issues. So I'll talk to you about using plasmas to accelerate electrons in very short distances to very high energies, and about techniques to increase the photon yield. This is an experiment. This is just simulations so far. But we guide laser pulses in plasma structures. So in principle, we can make a long laser pulse without having a large laser spot size, and that could help mitigate that issue of scattering, get us a lot of photons from a reasonably sized laser. And lastly, once we've made the photons, we've recently done a proof of principle experiment that shows that that same accelerating structure that we make can bring the energy of the electron back down. So that once we produce the photons we want, we can get rid of the high energy electrons without a lot of shielding. So let me go through that step by step. So this is the acceleration process. So what we do is we replace a conventional radio frequency accelerator structure, which has maximum ability to give energy gradient to particles of about 10 to 40 mega electron volts per meter. So again, for a 10 MeV beam, that's perfect. It's about a meter long. For a half GeV beam, it's tens of meters. So we replace that with a plasma structure that can give us very high gradients. And recently we've demonstrated, in fact, not so relevant to this application, but we can get up to 4 GeV electron beams in just a few centimeters, instead of in the tens of meters that it would take. And this is a recently published experiment. The question is, can that technology, which has primarily been developed up until now for high energy particle physics applications, HEP wants this, high energy physics wants this to build their next particle collider. can we apply that to make a photon source? So fundamentally, this is the accelerator experiment. So you have a vacuum chamber in which you have a jet of gas going upward, and you focus into that gas a little laser pulse that scoops up and accelerates electrons. So this is the cartoon version of that. See the gas jet here squirting up, and the laser pulse gets focused down into the gas jet. It ionizes the gas, making a plasma, and then accelerates some electrons. So how does it do that? If we zoom into that gas jet, this is the same picture that I just showed you on the other page. And if you look at what's actually happening around the laser pulse is sitting here. The vertical lines are the wave fronts of the laser pulse. This is a particle simulation of the process. And the laser pulse is propagating from left to right through the plasma, and its radiation pressure is intense enough that it actually displaces the electrons in the plasma. And so the blue scale is showing you the density of the electrons in the plasma. So the laser pulse goes through the plasma, displaces the electrons, leaving this white region where there are almost no electrons left. The ions for these laser parameters are too heavy to be moved by the laser. And so they pull the electrons back, and what you get looks very similar to the wake of a boat, but instead of being in the height of the water, it's in the density of the electrons. So ambient density driven out to near zero by the laser pulse. And then as the ions pull the electrons back, you get a very high density region, and then it oscillates with low density again. And of course, that density oscillation of the electrons means that there's an electric field. And the electric field, it turns out, can be extremely strong. Let's see, we'll skip the animation there. And so the analogy, again, is just sort of the wake of a boat. A boat goes through the water, digs a hole in the water, and that creates a potential gradient. I don't know if you can see the person there, but you can actually surf on the wake of a boat in addition to water skiing on it, riding down the wave. And so that's the principle that we exploit. The laser expels the electrons, making this potential structure, and then electrons can be trapped in that structure and accelerated to high energy. So this is going to be the movie version of that, and you'll see the boat on the left and the plasma on the right. Let's see if we can make these run. So the laser pulse focuses and drives the wake and eventually traps particles. And similarly, the boat goes through the water and drives a wake, and eventually he can let go of the rope and be injected into the wake. So that's a process that's been demonstrated for many years now. And in 2004, we got the first beams ever from this kind of accelerator to have narrow energy spread. So these were 100 MeV beams. And over the ensuing years, we've increased them to a GeV, and as I showed you, 4 GeV. But the problem with these results from the point of view of a photon source for controlling that scattering process is that they were never stable. They were never controllable. And so that would never make a photon source. And the reason comes down to how we did it. We did what amounts to a tsunami or a big ocean wave breaking on the beach. We just drove the wave up to higher and higher amplitudes until eventually it broke, which means that it achieves an amplitude sufficient to scoop particles up and throw them forward. So some of those particles are nicely phased and they gain energy, and some of them are not so nicely phased. And so that drove fluctuation, essentially. If you drive things just right, your particles get the right amount of energy, but any fluctuation, any tiny change in parameter will disrupt them. And so what we did over the last few years is to separately control the parts of the process. And this is an example of doing that really in a simple way. This is that same gas jet, but now you just put a little blade in it. It's literally a razor blade. And that razor blade creates a shock in the gas jet. And if you look at the density along this axis, it goes up and then it drops at the shock. And what that corresponds to is it actually, if you think about the plasma wave, that changes the period of the plasma wave when you hit this shock, and you'll see it. Here's the wave being driven. It has a pretty constant length, and as you come to the shock, boom, it expands. And that expansion triggers the injection of particles in a controllable way. The result was that using that technology, you could control the energy of the particles, and you could control them in a reproducible way. Here, the error bars are showing you not the error for a particular shot, but the fluctuation from shot to shot. So we now have a beam that's reproducible from shot to shot, and whose energy can be controlled over a wide range. In this case, just by changing the position of this blade in the jet. And that's one example. I won't go through them all, but over the past few years, we've demonstrated a lot of other properties that would allow us to make a photon source. We've demonstrated that we can get high energies from a relatively small laser. We've demonstrated that the divergence of our beams, its emittance effectively, is competitive with state-of-the-art radio frequency Linux. We actually get the same number that they get down at LCLS, for those of you who are accelerator geeks. That's the newest accelerator for the Office of Science. That we can tune the energy at the half GeV level, and that we could get 1% level energy spreads. And we've also shown that we can make accelerators that operate over days and days of operation. So this is another example of consecutive energy spectra taken, showing you the stability of the energy and of the charge of the accelerator. So the point of that is that we're coming to the point where these accelerators are not just experiments that we publish on their own, but that you could use them for something. And that's true not just in the energy, but in the pointing. This shows you a phosphor screen image of the electron beam. We can control the pointing, and we can control it both in the X and the Y direction. So this shows you that we can scan, that is, we can control where the beam is pointing. So with that, we could then consider making a photon source. And so we simulated what could we do. And these are simulations of what photons would be produced from the experimental electron beams that I've shown you on the last few pages. And indeed, it looks like we can make photon beams in the MeV range at energy spreads of 10 to 20%. And those energy spreads are coming primarily not from the energy width of the electron beam, but from its divergence. And so if we were to refocus that electron beam to reduce its divergence, we can in principle drop down to the 1% or 2% level photon beam energy spread. So that starts to look like we have the tools to make a high quality monoenergetic photon source. We'd still need to address the yield of photons. How can we make a large number of photons from a realistic number of electrons? And the issue again is that typically you need a large laser spot, and that ends up wasting your laser energy. And so what we hope to do is to apply the same technology we use for the accelerator. That is, we make a waveguide in the plasma that now when we focus the laser tightly, it maintains that focus for a long distance. And that can drop down the energy required to make a given number of photons by more than an order of magnitude. And this energy, the 1 joule level, is sort of compatible with what we use to accelerate the particles. So it's a reasonably balanced system where we're not being dominated either by the accelerator or the scattering laser. And I should point out there are sort of more advanced techniques by shaping the laser, but I won't talk about those too much. So lastly, we're going to end up with a half GeV electron beam. I think this was really one of the things that stopped people from thinking about this kind of technology for nonproliferation. Because if you have a nice MeV photon source with a half GeV bremsstrahlung source attached to it, you're kind of sunk. So the concept is to deaccelerate the electrons after you use them, and to do that using the same plasma structure. So it turns out nature is very kind to us in this way, because the laser that's driving our plasma structure will travel slightly slower than the vacuum speed of light through the plasma. The group velocity of a laser in any medium is always less than the vacuum speed of light. So what that means is that if I initially put a particle, this is that same wake structure that I showed you before, if I put it in the blue part, which is accelerating, over distance it will gradually slip forward in the accelerating structure. And it'll slip first to the null of fields, and if I look at the trajectory, the energy is a function of distance, it'll accelerate, it'll stop accelerating, and eventually it'll slip into the deaccelerating phase of the wake. And its energy should come back down. So the question is, will it? And so we did an experiment to find that out. And as part of that experiment, we also realized that if you flow a current in the plasma, you can additionally create a focusing lens. Some of you may be familiar with magnetic focusing optics that are used for electron beams. This provides a much more compact tool. So what we did was we combined essentially 3 plasmas. One is that very stable accelerator that I showed you previously. The second is a plasma that has a current flowing in it to act as a lens. So that takes our diverging electron beam, refocuses it to a second plasma. And that second plasma we powered with a second laser pulse. And the reason that we did that is that now by controlling the timing of this laser pulse, we control where that electron beam is sitting in the second accelerator structure. And so this is the reference. We can put it in the accelerating phase and increase its energy. We can put it in the deaccelerating phase and decrease its energy. And we can repeat that for various phases. That is, you should have multiple accelerator buckets behind the laser pulse. And indeed, this is the first bucket and the second bucket. So that proved that we could combine two plasma accelerators and that we could use them to either increase the energy, which we care about for high energy physics, or that we could use it to decrease the energy. And we're still at the point of doing proof of principle. The simulations indicate that if we do it right, we should be able to extract more than 90% of the electron beam energy. So that's the next step. So our current project that we're doing right now at the lab is to put all of those elements together. These are all the things that I just walked you through: accelerator, scattering, and deacceleration. So we've done independent things, and so what we're now doing is trying to integrate all those together to make a single experiment that demonstrates that all of that works as one system. And so we've just completed building a new laboratory up at the lab with an area for the laser, an area for the photon beam experiments. So that's what that looks like. There's a laser room, a photon source room, and then an area for experiments using the photon source. And the idea will be to combine all of those techniques that I just showed you: the accelerator, photon production, and deacceleration. So we've just completed the facility and we're installing the laser. And we anticipate making photons this year and then having a 2-year program of experiments going forward. One component of that, as I mentioned, Yigang Zhang is a student at Cal working with us on detectors. These photon beams are very difficult for detectors because all of the photons are produced in a femtosecond long burst, the intersection of the laser and the electron beam. And so a typical high purity germanium detector will be very inefficient. You get only 1 photon per shot. The concept that Yigang is developing is to scatter that photon beam in a foil and then detect the resulting Compton scattered electrons to be able to characterize the beam in 1 or in a few shots. So that's the project that we have going on now. The last slides I want to show you is how we envision that going from where we are now, which is in the lab, out into the field. So you saw the facility we have now. We occupy about 30 square meters of optical table, which is already not too far off the size of a large truck. But the kind of laser that we use is actually used for other things. And this is an example. Amplitude Technologies, which is a French company, sells a laser of the type that we use that they trailer around behind a car and use for atmospheric sensing. And you can imagine putting a couple of those into a U-Haul, one to drive the accelerator and one for scattering. And so you could at least envision that if we're successful, you could take this kind of thing out into the field, where a field is defined by being accessible to something like a U-Haul. But I think I told you that for the applications assessments that we did, you need at the order of kilohertz repetition rates to deliver the kind of fluxes that you need. These kinds of lasers right now only run at a few hertz repetition rate, up to 10 hertz. And so there is a parallel program that's not really part of the project that we're working on. But as I mentioned, this development is primarily driven by the Office of Science towards future high energy physics colliders. And so there's a large effort underway to scale these lasers to kilohertz. And that's also impacted by things like directed energy weapons and other uses of high energy pulse lasers. And so that's essentially the path forward. If we're successful in the demonstration we're doing the next couple of years, our next steps will be to scale it to kilohertz and then to improve all of the properties, that is, increase the accelerator charge, make the energy spread narrower, and in that way push the performance from 10% energy spread level down to 1% energy spread and to increase the yield. And as I think I mentioned at the start, that has the potential to impact a lot of things. We've talked about nonproliferation, but medical and industrial radiography would benefit from the same kinds of things. And this is all part of a program developing these kinds of accelerators for a broad variety of applications. This is the big one, which is a future high energy physics collider. And the application requirements that I've talked about here are pretty challenging. Kilohertz level, half GeV. This is orders of magnitude beyond. That would be multiple TeV, multiple tens of kilohertz, much higher charges. On the other hand, of course, this would be a large facility. So I think that's all I have to say. And I just want to close and welcome your questions and just say we have 2 student projects in progress right now. Yigang Zhang working on detectors, and Cameron Miller, who worked with us on the safeguards application and who is now transitioning to start work on dosimetry and other essentially experiments with the photon beam. So if any of you think this is interesting, I'd love to talk to you. Everyone from physicists who'd like to do the laser plasma acceleration physics to people who'd like to do things with photon beam. Great. Questions? Yeah.
How do you deal with pair production out of curiosity if that occurs, since you're dealing with photons higher than 1 MeV?
That's right. So the ratio between pair and Compton processes is actually a signature that people are starting to use. So it's essentially an attenuation mechanism, right, and scattering mechanism for the photon beam through the target. So in one sense, the answer to that is that's part of the attenuation curve that I showed you, right? So that's part of what you're measuring. So that's the sort of the gross level, and that's what people usually use at this point. There's one system that's trying to do more than that, which is the Passport EZ3D system, which is using a bremsstrahlung source, but instead of just measuring transmission, so if you measure transmission, you're essentially convolving all of the processes that affect the photon beam. But if in addition to transmission, you measure backscatter or near backscatter, the angular distributions for the various processes vary. And so by measuring both transmission and near backscatter, they're essentially exploiting the ratio between pair and Compton, and in that way they can get a very sensitive Z measurement. And so it's one of the things that would be of interest. If you were to develop a monoenergetic source, you could do exactly the same thing. You'd have the benefit of isolating an energy. You'd have the problem that the way that they do it is they use energy resolving detectors, so essentially counting detectors. And that would be very difficult to do with a pulsed source. So the ideal thing, you might have a few different, for example, Cherenkov detectors or some other type of detector that have energy thresholds. So you might be able to do it that way. Or you might have other approaches to doing that energy resolution. But yeah.
Okay. And out of curiosity, like, how sensitive do you think you'd be able to determine compositions of, say, like fuel cells or like waste buckets or something?
Right. So doing that really would rely on nuclear resonance fluorescence. And if you're doing nuclear resonance fluorescence, it's really limited by the amount of time that you want to wait. In principle, people have done nuclear resonance fluorescence measurements that are very sensitive to isotopics and very sensitive to composition. And so, for example, the measurements that I showed you for treaty verification, which I went over very fast, but they were devoted to things like that. For example, can you tell that this is, for example, HMX explosive? And you can, given minute measurement times. And so a fuel cell would be something similar. You'd define, what it's sensitive to, of course, is the number of atoms of a particular isotope that are present, right? So you can't tell anything about chemical composition. All you can tell is sort of, how many nitrogens, how many carbons, how many U-235s, things like that. Yeah. Good. Any other questions? Yeah, please.
You said the electrons kicked off by the terawatt laser radiation pressure.
Yeah.
Does that have strong electric field? Like, what's the the order of magnitude of the field? Does that present like any unforeseen problems?
Yeah. So the intensities at which this works are essentially the intensities at which the electron oscillation in the laser field is relativistic, but the ion oscillation is not, right? Because you want to avoid pushing the ions. So that corresponds to intensities in the range of a few 10 to the 18 to a few 10 to the 19 watts per square centimeter. So that's well above the intensities that are required to ionize hydrogen. It's nowhere near the intensities that would be required to fully ionize something like nitrogen. And so the main thing that's perhaps interesting about that is that it pretty much limits you to low Z gases as your target. Because if you were to use something like nitrogen, you would ionize it to some degree near the center of the laser and less outside, less in the periphery of the laser beam, a larger radius. And it turns out that a plasma with that structure, that is with peaked density on axis and then density falling off, is a defocusing lens. And so that would severely limit the length over which you could drive the process. So people have done certain things with, for example, doping very small amounts of nitrogen into the target. And that can be useful because you then exploit that ionization as a way to inject particles, but you wouldn't use it as the bulk target. And the intensities are low enough that really ionization is probably the most interesting thing that happens. I mean, there's all sorts of discussion right now of what will happen with sort of the next generation of lasers when we go to a few or 10 petawatts and we're able to focus to intensities in the mid-20s per centimeter squared. And there you start to be able to think about things like breaking the vacuum, nonlinear QED processes, and eventually pair cascades, where you would produce a pair and then produce a cascade of pairs. And so there's a lot of interest directed at higher intensity lasers for that purpose, but not at these intensities. In fact, somewhat we have to avoid those intensities for this process to be active. So you'd asked about the electron acceleration process. Did I get at what you were asking about? Good, good.
Any other questions? Did everyone have a chance to put your email address down on this? I don't think I got you. So I'll be sure that everyone has each other's contact information.
Okay, good.
I have a question.
Yeah, please.
So in your facility, what is the main technical processes you work on there?
Yeah.
Did you test the spread mostly? Or
So the largest portion of effort in the first 2 years has been literally buying and building the laser. So the experiments that I described to you were conducted on laser that's almost 20 years old, which in laser terms, lasers are kind of like computers at this point. So it's quite old. And because it was quite old, it did not fit all into that nice laser room adjacent to the experimental area. It was spread over 2 floors. So while it delivered sufficient stability to do the accelerator experiment, it wouldn't have delivered sufficient stability to do the intersection and scattering experiment. Moreover, you want a very different laser pulse to do the accelerator drive. You want it to be very short to resonantly drive that wave versus the scattering process, which needs to be longer and preferably narrower in spread in frequency. So the new laser is designed to deliver both of those things. It implements sort of the state-of-the-art lasers to allow it to be smaller. It's shrunk by about a factor of 3 in comparison to our old system. And then it implements 2 beam lines, one for the drive laser and one for the scattering laser, that have separate techniques. So that's been our largest effort over the last 2 years. And it's a pretty big capital purchase, so we've had to spread that out. The government doesn't like to give you lots of money at the start, right? They like to spread it out. And so that's the reason why those deacceleration experiments that I showed you, those were the experiments that we did in the first year and a half. So what we did was we made a sort of a separate area where we could build the laser, did experiments on the old laser while we built the new laser. And we've just, in the past couple of months, cleared out the old laser. So we're no longer doing any experiments at this point, and we're beginning installation of the new laser. In fact, today is the first day of operation of the new laser in its new home, which is exciting. I'm going to go back up the hill, hopefully, and turn it on for the first time. And so once it is operational, which will be in the next few months, then most of the work of the project on my side is making the accelerator work, making the guiding of the scattering laser work to increase the yield of scattered photons, and then the deacceleration process using either a second plasma or a continuation of the first plasma. And that's the largest part of the experiment, to be honest. But at the end of the day, we'll produce photons, and we have to then characterize them and prove that we've generated what we said that we would and that it makes sense. And so that's the reason for the detector components that I talked about. So we'll build some of those detectors ourselves, that spectrometer that Yigong is working on with Brian Queter and others. And then other detectors will get brought by others. The Idaho group is going to bring several diagnostics that they've used. They've done a lot of the tests that we're talking about using bremsstrahlung beams. There's a facility at Idaho that's essentially devoted to interrogation using photon beams with bremsstrahlung beams. So they'll bring out a lot of the detectors they've used. And then Cameron will bring some of his from Sarah Posey's group at Michigan. So that'll be, I would say, the sort of the later part of the project, starting mid this year and going for the next 2.5 years. We'll be doing experiments with the photon beam, proving that we can characterize it and that we understand how it scales with the performance of the accelerator. essentially.
So the part environment, the acceleration of electrons is already pretty solid.
So it was solid on the old laser. Of course, we're going to have to resurrect it, which is always, as you know, a project. But we believe that we know what has to be done to get the electron beams required. That does not mean it's not going to be work. It's definitely going to be work. But if I can put it that way, the accelerator performance we need is accelerator performance we have demonstrated. We just have to replicate it. Yeah. It's not an advance in accelerator technology. When we go to 1% photon energy spread, if we want to go down, and that will be an advance. Yeah. Not so much in the energy spread of the accelerator, but in its divergence. And that's actually one of the reasons why that little plasma lens that we used on our deacceleration experiment is important. We had to have it to couple from the accelerator to the deaccelerator, but also we can use it to refocus the electron beam for lower energy spread sources. Yeah.
Explain a little more the other student, the one who was not working on this section.
Yeah. Yeah, so Yigong Zhang is the student. He's a Cal student. He's working on the spectrometer. Cameron Miller is a student in Sarah Posey's group, and he's done two main things, he has done one main thing. He's transitioning to a second one. The thing he's done is the simulations of the cask scanning application. And the thing that he will do is he will bring detectors that have been developed at Michigan and use them to measure the photon beam, and specifically to do dosimetry measurements. They have both done, we're not the only group doing this. So they've done experiments at Nebraska, which is the other leading group in this area. So they'll do experiments to compare to that source. And then they also have a 9 MeV LINAC bremsstrahlung source that they're in the process of installing at Michigan. So one of the things that he'd like to do is, the simulations predict, for example, that you reduce scattering using the monoenergetic narrow divergence source, and that impacts both signal quality and the amount of radiation that gets scattered into the environment, and that would affect, for example, bystander dose and the exclusion zone you'd have to set up around a system, which is particularly important, like in a port where you don't want to have people walking by. So he has dosimetry measurements that he's going to bring. They'll do measurements on their LINAC, and they'll do measurements here. All right. If anyone else has more questions, I'll be around for a few minutes, and you'll have my email. I'd be happy to talk to any of you.